My name's Tom Dick. I'm a math professor and math advisor for Texas Instruments, and this short video is part of the TI-Focus AP Calculus series. We're going to be using the TI-Nspire to look at an example quite similar to a problem found on the 2020 AB exam that involved analyzing functions through a graph. The graph presented here is piecewise, made of line segments and quarter circles. Now, no formula was given for this graph, but to produce it on the TI-Nspire, I did need to come up with a formula for it. I'm going to show that to you here as f1 of x. You can see there's the linear piece over the interval from -2 to 0. Got a couple of square roots of quadratics, and then those are those quarter circles, and then two more linear pieces to wind up the function formula. So it's a very complicated analytic formula because it has 5 different pieces to it. But many of the questions we could ask about this would be answerable geometrically. Now I'm going to go ahead and pull up the attributes of the axes and get more labels on this graph. So now we have all the tick marks on the two axes labeled. And now let's look at some of the questions that we could answer. What would the graph of the derivative of this function look like? Well, here we have a constant slope of -2. So our derivative graph should have a horizontal line segment at the height, -2. On this piece of the quarter circle, it starts out very steep, positive, comes down to 0. The same with the next quarter circle. We should see those values reflected in the derivatives graph. And again, where we have line segments, those have constant slopes, and so those should correspond to constant y values on the derivative over those intervals. Now we're going to check our thinking here by taking a look at the derivative of that complicated piecewise function. So I'm going to pull up f2 of x, bring up my derivative template, enter that. And remember, our complicated formula is in f1 of x. So I'm going to take the derivative with respect to x of f1 of x, and then that will produce a graph for us of the derivative. All right, let's take a look and see if our thinking matches what the derivative graph looks like. Now, the way the TI-Nspire graphs is, rather than graphing from left to right, it's actually doing some sampling of values. And so we're seeing the graph come up over time, and it's filling out as we look at it. Takes some time because of the piecewise nature of this particular function. But we'll wait a bit here, and we're almost done. And then we can take a look and see if our analysis made sense. There we go. Now over that first interval, where we were talking about a constant slope of -2, sure enough, the derivative graph in red is a horizontal line segment at -2. The quarter circle starts out very steep positive, a high positive value, coming down to 0. The next quarter circle, very similar, stretched over a slightly larger interval though. And then these two linear pieces should correspond to horizontal pieces on our derivative graph. One of these had a slope of -3/2, the other +3/2, and so we're seeing horizontal line segments at y value -3/2 and +3/2. All right, now I'm going to turn off that derivative, and now we're going to take a look at an antiderivative. In other words, suppose this blue graph is the graph of the derivative. So we're going to take a look at an antiderivative of this function. So I'm going to pull up the definite integral template, put that into f2, and then we're going to use a lower limit of 0. An upper limit is going to be our variable x, and then we're going to be integrating our blue graph function, which is f1 of t dt. And now we'll take a look at the antiderivative graph and try to reason from this graph, does this make sense? Okay. Well, let's take a look. Where my function, blue function, changes sign from positive to negative at -1, we should see a maximum in our red graph. And where our blue graph changes from decreasing to increasing, well, that's going to be a change in concavity in our red graph. So you see an inflection point at 0. Where those two quarter circles join is also where that blue graph crosses the axis, changes from negative to positive. That's the location of a local minimum. And let's take a look. We've got a couple of other places where the blue graph changes from increasing to decreasing or decreasing to increasing. Those should be inflection points in our red graph. I'm going to drag down the graphing window here, and at x = 5, that's where we should see one inflection point. That's very subtle. At 7 we have a more obvious inflection point, but this is all making sense in terms of what the antiderivative graph should look like. All right, let's go ahead and move the graph back up again. Here's the point I'd like to stress here. This problem is really intended for us to interpret the behavior of the derivative of a function as well as the behavior of its antiderivative simply by considering the graph of that function. We use the analytic form on the Nspire so that we could get some visual confirmation of that reasoning. Well, that winds up this short video. For more resources like these, please see education.ti.com.